Welcome to the lecture on Climate Intervention Strategies, or Geoengineering, using CESM and in particular WACCM. We as humans intervene in the Earth's climate for a long time. For example, the Industrial Revolution has caused cooling of the Earth's surface due to increasing pollution and particles in the atmosphere. In addition, increasing emissions of anthropogenic greenhouse gases result in increasing surface temperatures at an unprecedented speed. These relatively small changes in temperature change the balance of the Earth and our ability to sustain our way of life in the future. Signals of climate change become more and more imminent, and we experience already these unprecedented weather events, shift in rainfall pattern, heat waves, mass extinctions, melting of sea ice and land ice, and sea level rise. In order to address these changes, various climate solutions have been suggested, including various ways of renewable energy production that have to be strongly ramped up. However, in order to reach important temperature goals and to prevent worst impacts, ambitious mitigation may still not be sufficient. Climate intervention or geoengineering strategies have been proposed, including methods to remove carbon dioxide from the atmosphere. Another method is to reflect some of the sunlight and that will cool the Earth's surface. One suggested method is increasing stratospheric aerosols in order to reflect some sunlight, also called stratospheric aerosol intervention. This method is based on natural analogues. The eruption of large volcanoes has injected large amount of sulfur into the stratosphere, which resulted in significant increase of stratospheric sulfate. The surface temperature anomalies with regard to 1970 conditions is showing a measurable decrease in surface temperatures after large volcanic eruptions. To research stratospheric aerosol interventions, it requires to use a tool that is actually able to resolve processes important for these applications. Fully coupled Earth system models, like CESM, are used because they couple various components, atmosphere, land, ocean, cryosphere, in order to fully simulate climate feedbacks and the impacts on the climate. These models need to be driven by natural anthropogenic forces and have to be able to reproduce the historical climate well, including the cooling effects of large volcanoes. For stratospheric aerosol interventions, a model in particular has to include a well-resolved stratosphere, including comprehensive stratospheric dynamics and chemistry, and aerosol microphysics, as well as coupling to radiation. CESM WACCM is a model that is well suited to be used for researching stratospheric aerosol intervention. It has a sufficient horizontal and vertical resolution, a model top that reaches up to 140 kilometers, and it resolves important dynamical processes, including the Quasi biennial oscillation. It has interactive chemistry and prognostic aerosols, and is a fully coupled Earth system model. Simulation of stratospheric aerosol intervention with WACCM have been performed in recent years. In particular, continuous sulfur injections have been placed at 4 locations in the stratosphere, at 15 north, 15 south, 30 north, and 30 south, in about 20 to 25 kilometers. This has been done in order to adjust the resulting sulfate layer in the stratosphere to reach specific surface temperature goals and objectives. Those goals include global surface temperature, as well as interhemispheric and pole to equator temperature gradients. In order to reach those targets, a feedback control algorithm has been applied to adjust the amount of injections at each of the locations. This is done because it has been shown that reaching those temperature targets can help to reduce some of the side effects of stratospheric aerosol intervention. This movie shows the movement and accumulation of stratospheric aerosols after sulfur injections at the 4 locations in the stratosphere. First, we can see the movement of the tropospheric aerosols before the injection in January 2022. The first injection occurs in 50 north. One can see nicely how the aerosols are distributed quickly around the injection longitude and then further distributed over the poles. In 2023, injection at other locations starting, including and filling up the entire globe in the southern hemisphere. With continuous increasing emissions, the aerosol layer is getting thicker and able to reflect more sunlight back into space. The application of sulfur injections has been tested using the high emission scenario RCP 8.5 and the goal to keep surface temperatures to 2020 conditions. On the left on the slide, one can see that with our approach, the three temperature goals could be achieved. In black, we can see the RCP 8.5 temperature changes for global surface temperature on the top, as well as interhemispheric temperatures in the middle and pole to equator temperatures at the bottom. In blue, we can see that the stratospheric aerosol intervention approach was able to keep these temperatures at about 2020 conditions. On the right, we see the increasing sulfur injections in teragram SO2 per year, in black for the total injection amount and in colors for the different injection locations. In order to counter the warming of RCP 8.5 by the end of the 21st century, one would require a huge amount of annual injections that is equivalent to 4 times the amount of Mount Pinatubo eruption in 1991. This scenario is not realistic, since increasing emissions will strongly increase the risk of determination. This means that if stratospheric aerosol intervention would be suddenly stopped, surface temperatures would go back to warm temperatures in a very short time, about 10 years, and that would result in large changes to the climate system. We have performed a 20-member ensemble of this simulation and allowed to assess and investigate the climate impacts of these approaches, including identifying robust signals within the climate variability. The so-called Geoengineering Large Ensemble Project, or GLENS, has been used for various impact analysis. In the next slide, there are just a couple results that we are comparing changes with regard to 2020 baseline conditions. First of all, we look at surface air temperatures, which compare conditions from 2075 to 2095 minus 2010 to 2030. On the left, we see the strong increase in temperatures in the RCP 8.5 scenario. On the right, we see that there are almost no changes in the stratospheric aerosol intervention application. However, there are still some signals, for instance, a robust warming over Eurasia in winter, and this process has been also shown in other previous studies. Looking at changes in precipitation, which are again referred to 2020 conditions, we see large changes for RCP 8.5 on the left. And those changes are in particular over Northern Europe and Asia, as well as North America and South America. On the right, we see the changes for stratospheric aerosol intervention experiments, and there are much fewer changes, those are in particular over the oceans. However, some changes are visible, in particular the decrease in rainfall over India and Amazonia, as well as increases in rainfall over Australia. Since we are increasing the amount of sulfate in the stratosphere, which is right in the middle of the ozone layer, we have to be concerned about impacts on the stratosphere composition, in particular ozone. There will be a new chapter in the WMO 2020 ozone assessment looking in particular on the effects of stratospheric aerosol intervention on stratospheric ozone. The increase in stratospheric sulfate will lead to two important changes. One is the increase in stratospheric aerosol surface area density, shown on the middle top panel, which impacts the chemistry in the stratosphere, as can be seen on the right top. Changes in the importance of ozone-destroying cycles result in changes in net chemical production of ozone. Second, sulfate aerosols absorb, in particular in the long wave, and result in stratospheric heating. The temperature changes can be seen on the bottom left of this panel. This can in turn result in changes in water vapor as well as changes in transport. The Antarctic ozone hole, which reached the lowest values of total column ozone in recent years, is expected to recover by the mid of the 21st centuries. The figure on the top left shows changes in total column ozone in the RCP 8.5 scenario in black and the stratospheric aerosol intervention scenario in blue. Those results are based on the GLENS results. the results are showing that the recovery of the ozone layer is delayed until the end of the 21st century with stratospheric aerosol interventions. Looking at other areas of the globe, in the northern hemisphere high latitudes in March, for example, on the top right, stratospheric aerosol intervention will lead to some reduction in total column ozone, in particular at the beginning of the application, but not so much towards the end of the 21st century. Other parts of the globe, including the tropics or northern hemisphere mid-latitudes in winter, may experience increases in column ozone compared to RCP 8.5. Both increasing and decreasing ozone values change UV and may be problematic as they both come with negative side effects and health effects for both ecosystem and humans. Stratospheric aerosol intervention also impacts stratospheric dynamics, in particular the Quasi-Biennial Oscillation or QBO. What you can see on the top is an experiment where we did not inject at the 4-point locations like GLENS on the bottom, but just at the equator. Depending on the injection location, the QBO might actually shut down with stratospheric aerosol interventions, as can be seen here after the onset of the injections. On the bottom, we see that in GLENS, the QBO is not actually shutting down, but it does slightly change the speed towards the end of the 21st century. Changes in the dynamics may be very important and have to be looked at in much more detail. As mentioned earlier, GLENS results have been used for various studies, but this model experiment is not considered realistic. Increasing greenhouse gases, as assumed in RCP 8.5, require continuous injection to keep surface temperatures at desired level and increase the risk of termination. To reduce the risks and also impacts of these applications, we need to consider a portfolio of climate intervention strategies. In particular, significant mitigation is required to reduce greenhouse gases. Further, reductions in carbon dioxide may be achieved by negative emissions like carbon dioxide removal techniques. At ENCA, we have performed some more policy-relevant studies, including a peak shaving scenario. In those studies, we assumed a late mitigation and carbonization scenario after 2040. This results in the so-called overshoot case, where greenhouse gases and temperature overshoot a desired temperature target by some amount in some time. Stratospheric aerosol interventions would then be used to shave this peak and reduce some of the impacts of climate change. This also would result in reduced amounts of sulfur injections which are required and potentially result in less impacts than what was shown for GLENS. More realistic scenarios have to be still developed that consider the physical limitation as well as deployment costs and efficiency. More help from the community is also needed to analyze already existing results and scenarios and also those that will be provided in the future. In particular, we want to look at impact and risks. If you're interested in these type of simulations, please contact us. Thank you very much.